Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant. And a special hello to all of you at Ishik Boys High School, particularly Mr. Jager's students.
Hey, everyone.
Today we're doing a deep dive into something really central to electricity. We're talking electrical potential energy, electric potential, and potential difference.
Yeah, these sound maybe a bit technical, but honestly, they're what makes everything tick electrically. Your phone, your lights, even cars. It's fundamental stuff.
Totally. And our goal today is to, make these ideas clear, show you how they pop up in your daily life, and hopefully connect them right back to what you're learning in class.
Let's do it.
Okay, first up, electrical potential energy. You might see it written as PE, subscript electric.
Right.
So what is it? Well, simply put, it's the energy a charged object has just because of where it is, its position inside an electric field.
It helps, I think, to compare it to gravity. You know, like a ball you're holding up high. It has gravitational potential energy because it's high up in Earth's field. It's got stored energy, ready to go.
Right. So electrical potential energy is, well, it's a very similar idea. But instead of gravity and mass, it's about electric charges interacting.
Exactly. How close they are, the field they're in, that sets their stored electrical energy.
It's like this hidden potential,
Yeah.
Ready to make something happen electrically. A tiny spark or even, well, lightning. Stored readiness.
And it's actually part of a bigger energy picture, what we call mechanical energy.
Oh yeah, that's important. So
Yeah.
it sits alongside kinetic energy, that's energy of motion, and gravitational potential energy, like the ball example,
Yeah.
and elastic potential energy, like a
Yeah.
stretched rubber band.
All of these different types of energy.
And when you add them all up, kinetic, gravitational, elastic, and our new one, electrical potential energy,
Yeah.
you get the total mechanical energy.
And the really key idea, especially for your physics class, is that if you ignore things like friction or maybe energy radiating away as heat or light,
Yeah, the non-conservative force.
right, then that total mechanical energy, it stays constant, it's conserved.
It just changes form, right? Doesn't vanish. Doesn't appear out of nowhere.
Precisely, it just converts between those different types.
So what happens when that electrical force actually, moves a charge?
Well, that's when work is done on the charge. The energy changes.
Can you give us an example? Maybe something visual?
Sure, think about a Tesla coil. You've seen pictures, right? Those big sparks flying off.
Yeah, they're amazing.
So negative charges are pushed away from the center part. They move out towards the air or the walls. As they move, their electrical potential energy goes down.
Oh, okay. Like letting the ball fall, its gravitational potential energy goes down.
Exactly like that. The potential energy gets converted as work is done moving the charge.
Okay, that makes sense. Now, what about inside a uniform electric field? That sounds a bit more well-structured.
Yeah, it's a really useful model. Imagine two big, flat metal plates parallel to each other. One's positive, one's negative.
Right.
Between those plates, the electric field is pretty much the same strength and points in the same direction everywhere. That's uniform.
So if a charge moves in that field, how does its potential energy change?
Well, the change depends on three things. One, how much charge it has, the magnitude. Two, how strong that electric field is. And three, critically, how far it moves parallel to the field lines.
Okay, so parallel is the key direction. Like pushing something up a ramp, the distance up the ramp matters for potential energy gain, not just moving it sideways.
Exactly that. And the unit for this energy, like all energy, is the joule, capital J.
Right, the joule. Makes sense. So if I move to charge sideways, like perpendicular to the field lines.
Good question. In that case, the field does no work on the charge.
So no change in electrical potential energy.
Correct. It's like sliding that book across the shelf instead of lifting it up or down. Its gravitational potential energy stays the same. You have to move with or against the field direction for the electrical potential energy to change.
Okay, this electrical potential energy seems great for talking about one specific charge. But you mentioned the field. What if we want to describe the electrical environment itself without needing a charge there?
Excellent point. That's precisely why we need another concept. Because potential energy depends on the charge you put there. To talk about the field itself, we use something called electric potential.
Electric potential, okay. Symbol V.
Usually, yeah. Capital V. And what it represents is kind of the electrical energy per unit charge at a specific point in space.
Energy per charge. So you take the electrical potential energy a charge would have at that point
Uh-huh.
and divide it by the charge's own magnitude.
Exactly. So now you have a property of the location in the field. It tells you the potential energy waiting there for each coulomb of charge you might place there. It's about the spot, not the particle.
That's a neat idea. So every point in an electric field has its own electric potential value, like mapping out electrical heights.
Kind of, yeah. But just like height, the absolute value isn't always what matters most. What usually makes things happen, it's the difference in height.
Yeah. Okay. The difference between 2 points.
Precisely. And that's potential difference, also called voltage.
Voltage. Okay, I've definitely heard of that. So potential difference is voltage.
Yep. It's the change, the delta, BV, in electric potential between point A and point B.
And the unit for this is the volt. Also V. That's not confusing at all.
Yeah, a bit. But the unit volt, capital V, is named after Alessandro Volta. You know, the guy who made the first battery.
Oh, cool. So voltage is named after Volta. Makes sense.
And what 1 volt means is important. 1 volt is equal to 1 joule per coulomb.
1 joule per coulomb. So if I move 1 coulomb of charge across a potential difference of 1 volt,
It gains or loses exactly 1 joule of energy. It directly connects the push voltage to the energy chain.
okay, let's make this real. Batteries, like in my TV remote.
Uh-huh. A typical AA or AAA battery. That gives you about 1.5 volts potential difference between its ends.
1.5 volts. And a car battery. That's bigger.
A much bigger push, usually around 13.2 volts when fully charged. That potential difference, that voltage, is what drives the charge through the car circuits.
Got it. So higher voltage, more push for the charges.
Essentially, yes. More energy change per unit of charge moving between those 2 points.
And you said, like, with potential energy, only the difference matters.
That's right. The absolute value of electric potential at a single point depends on where you decide zero potential is. It's arbitrary. But the difference between 2 points is always the same, regardless of your zero reference.
Yet zero reference. I've heard of grounding things. Is that related?
Exactly. Very often, especially in circuits, we just define the Earth as having zero electric potential.
Ah, so Earth is the baseline.
Yeah, it's a huge convenient conductor, so we call that 0 volts. Then we measure all other potentials in a circuit relative to that ground point.
Okay. Now, what if you have, like, lots of charges around? How do you find the electric potential at some point near all of them?
Good question. It's actually much simpler than finding the total electric field from multiple charges.
Oh, why is that? I remember adding electric fields involved vectors and directions. They got complicated.
Right. Fields are vectors. But potential and potential difference, they're scalars, just numbers. They can be positive or negative, but they don't have a direction in space.
Oh, nice. So no vector addition.
Nope. To find the total electric potential at a point due to several charges, you just calculate the potential caused by each charge individually,
Uh-huh.
and then you just add them up. Simple algebraic sum.
Wow, okay. That sounds way easier. Just need to be careful with the plus and minus signs of the charges themselves, I guess.
Absolutely. The sign of the charge determines the sign of the potential it creates. So you add the positive potentials and subtract the magnitudes of the negative ones.
Okay, scalar addition. Got it. That's a relief.
Makes life simpler sometimes.
All right, let's put this all together now with something we use all the time. Batteries. You said Volta invented the first one?
Well, the first practical one, yeah. Essentially, a battery is a device designed to do one main thing: maintain a constant potential difference, a voltage between its 2 connection points, its terminals.
How does it do that, though? What's
Oh.
going on inside?
Inside, there's chemistry at work. Specific chemical reactions happen that basically separate charges.
Separate them.
Yeah, they cause negative charges, electrons usually, to build up on one terminal, making it the negative terminal.
Okay.
And here's the clever part. Inside the battery, those chemical reactions actually do work on the charges. They push negative charges from the positive side towards the negative terminal.
Wait, negative charges normally want to get away from the negative terminal, right? Like charges repel.
Exactly. So the chemical reaction is forcing them uphill energetically. It's increasing their electrical potential energy.
It's like pumping water uphill into a tank.
That's a great analogy. The chemical energy is used to pump the charges up to a higher potential energy state at the negative terminal.
Okay, so they're pumped up, full of potential energy at the negative terminal. Then what?
Then, when you connect the battery to something, like a flashlight bulb,
You complete the circuit?
right, you give those high energy charges at the negative terminal a path to go somewhere they want to go towards the positive terminal, which is at a lower potential.
So they flow out of the negative terminal through the flashlight.
Yep, through the filament in the bulb, And as they flow through it, they give up that electrical potential energy they stored up.
And that energy turns into light and heat in the bulb.
Precisely. They run downhill energetically, converting their potential energy. By the time they reach the positive terminal, their electrical potential energy is back down to effectively zero relative to where they started inside.
And then the chemical pump inside takes over again.
Ready to pump them back up to the negative terminal as long as the chemical fuel lasts. It's a continuous cycle as long as the circuit is complete.
That also explains why a battery doesn't just run down sitting on a shelf, right?
Exactly. The chemical reaction provides the potential difference, but it really only does significant work and uses up its chemical fuel when charges are actually flowing through an external circuit, allowing the cycle to continue. It's not just a tank of electrons, it's an energy converter powered by chemistry.
Wow. Okay, that really connects potential energy and potential difference to something tangible.
It's a perfect example.
So let's quickly recap our deep dive. We looked at electrical potential energy, which is energy stored by a charge due to its position in a field.
Like the height analogy.
Then electric potential, which describes the energy per charge property of the field itself at a point, a scalar quantity.
Right, V.
And the crucial one for circuits, potential difference or voltage. That's the change in potential between 2 points, the push that drives charge, measured in volts. And we saw how batteries use chemical energy to create a potential difference, storing potential energy in charges, and then releasing it to power devices.
Nicely summarized.
All right, time for your reflection question. Think about plugging your phone into charge. How do these ideas, electrical, potential energy, and potential difference, explain how energy gets from the wall socket through the charger and into your phone's battery? Where's the energy uphill and downhill happening there?
Good one to ponder.
Stay in contact with your physics teacher. Stay creative.